In section 0.5, I will be discussing how to process data. By processing data, I mean to prepare it properly for presentation in a lab report and to analyze it. Part of that analysis will likely include the process of linearization. The video linked here shows another high school physics teacher discussing linearization in a little more detail than I'll do here. It's definitely worth a watch. In a lab experiment, after you've collected data, you will organize that data into a table. Typically, our data will consist of numerical measurements. There are several conventions that are important to follow when putting together a table. Each column should have a heading that shows the variable name along with the units of measure. Units should not be displayed within the table. Typically, we'll have the independent variable, that is, the variable that you physically change, should be listed in the column on the left. Data should be sorted within a column in ascending or increasing order according to the independent variable. This makes it easier for the person that's looking at it to get a better sense as to how the dependent variable changes with increases to the independent variable. In physics, we'll make use of graphs quite frequently. When you make a graph, you can use the graph shape and the equation of the best fit curve to infer the relationship between two variables. After the data has been plotted, you can draw a best fit curve, and the best fit curve is a graph of some function that best represents a mathematical model that fits our data. This is what a quality graph looks like, and I'll point out all the criteria that I believe a good graph should have. Graphs should have their axes labeled so that when someone looks at your graph, they know what data is being displayed. We should have a best fit curve or a best fit line that is applied along with its equation. You should try to format the graph so that it doesn't have a lot of wasted space, and the data should fill up most of the graph area. A good best fit is going to come very close to the plotted data. The best fit curve description in Logger Pro will automatically display two statistical tools that we won't use, but I'll discuss here briefly. The correlation is a statistical measure of how close the best fit line approximates your data. The closer to 1 that it is, the better your fit. A correlation of 1 would be a perfect fit. RMSE stands for root mean square error, and it's another statistical tool that shows how well a best fit curve lines up with your data. An RMSE of 0 is a perfect fit. If your graph is linear, then you can infer that the relationship between the variables is either linear or direct. It's direct if the y-intercept is 0 or close enough to 0 that we can say that it's negligible. Negligible means it's so small that we can neglect it or ignore it and treat it as though it's 0. You're almost always going to need to interpret the slope of a linear graph, and sometimes you'll have to interpret the y-intercept as well. For example, the slope of this distance versus time graph is 1.2 plus or minus 0.03 meters per second, and the units of the slope are often a good clue as to the meaning of the slope. And here they are meters per second. That should be a big clue that maybe we're talking about some sort of speed here, because meters per second is a unit of speed. The slope of a line is always equal to delta y over delta x, or rise over run. The rise, or the change in the y variable, is the distance. The run, or the change in the x variable, is the time interval. One of the first quantities that we'll define this year is speed. Well, speed is distance over time, so the slope of this graph is equal to speed, and the units of meters per second are consistent with this. Here, the value of the y-intercept is so small that we can say that it's negligible. Therefore, we can say that this linear graph passes through the origin, and so we can say that distance has a direct relationship with time. Well, what if the graph is not linear? Well, then you're going to have to linearize your data to make a linear graph. The process of this involves applying a simple function like squaring, cubing, square rooting, or taking the reciprocal. And usually we do this to the x variable or possibly to the y variable as well. And here, if we apply a squared function to the x variable, that can change the graph of y versus x into a linear graph of y versus x squared. There are several reasons to do this. It makes graphing by hand possible because all you need is a ruler to make that kind of graph. Drawing curved graphs is extremely difficult to do by hand. Also, you can be sure about the relationship between the variables once you've made a linear graph. The relationship between the variables of a linear graph will always be whatever's graphed on our y-axis is proportional to whatever is graphed on our x-axis, whether they're just the straight variables or whether they're functions of those variables. And lastly, linearizing helps cut down on random error in measurement, and that can increase the accuracy of your measured slope. The graph shape can help us decide the relationship, and we can do this by what's called inspection. And that means that we're going to take we're going to graph the data, and we're going to use the equation of the best fit curve to infer the relationship between the variables. So as an example, we're going to consider the data of distance traveled by an object accelerating from rest as a function of time. The data in the table shows that as time increases, the distance also increases. But does it increase linearly? Is it proportional to the square root of time? Is it proportional to the square of time? It's very difficult to tell just by looking at the raw numbers, and the graph shape can help us tell what the relationship is. The graph curves upwards, but to get the most accurate analysis of the relationship, we should apply a best fit curve to the graph. If the graph isn't linear, then 9 times out of 10, the trend line is going to be what's called a power fit. And a power fit makes logRPro calculate the exponent of the x variable. And you can use the value of this exponent to infer the relationship. Here, the power fit shows that logRPro has calculated the values of a and b, and it's the value of b that's the most important to us because that's the exponent. If we insert the values for a and b that logRPro calculated, you can see that the time is squared. And that's going to tell us that we have a square dependence, that distance will be proportional to time squared. I'm going to take a minute to remind you of some important values for exponents that you probably learned in algebra, but you've forgotten because you haven't seen it for a while. If logRPro tells you that the exponent is 0.5, you should recognize that that is an exponent of 1/2. And you should recognize that that's the same as a square root. So the relationship would be a square root dependence for an exponent of 0.5. If logRPro calculates the exponent to be -1, well, you should recognize that that exponent implies a reciprocal. This implies an inverse relationship. And if you have x to the -2 power, that's the same as 1 over x squared. And that shows that we would have a relationship that's an inverse squared relationship. We can also use something called theoretical analysis to help determine the relationship between variables. And hopefully, the relationship that you find by inspection will agree with what theory predicts should have happened in your experiment. The bulk of our learning this year is going to be about the best models that can describe relationships between variables. And these models are what we refer to as theory in a lab context. And we're going to learn this in class. Typically, you're going to use these models to form your hypothesis, and hopefully your hypothesis will be supported by the evidence that you collect in your lab experiments. If we continue with the example of the distance d traveled by an accelerating object as a function of time t, we have the equation d equals 1/2 at squared. And that models the relationship where a is the rate of the object's acceleration. By matching up the variables to the general form for a squared relationship, well, you can see that this model fits the pattern for square dependence, which is consistent with what we had with our analysis by inspection. So we should expect to see that we have a square dependence, that a graph of distance versus time squared is going to be linear. And this can also help us predict the slope of the graph. The slope of the graph should be equal to 1/2 the acceleration. So if we find the slope from a graph, we can use that to calculate the acceleration. We can take our distance and time data from before, and we can apply a function to the time data in order to linearize the graph. Instead of time, we're going to take time squared, and then we'll make a graph of distance versus time squared. The slope of this graph is predicted to be 1/2 the acceleration. So what we can do is take the slope data that's shown from Logger Pro and use that to calculate the acceleration. We can set the slope equal to 1/2 times the acceleration, plug in our value from the slope on the graph, and then we can calculate that the acceleration of this object is 3 meters per second squared.